So here's some stuff we're kind of talking about. Let me get this word out of here. Concavity tests. The graph of a twice, so you got to be able to take the second derivative in order for kind of this stuff to work. You know what I'm saying? You got to have a twice differentiable function in order to do this stuff. The graph is concave up on any interval when the second derivative is positive, and concave down on any interval where the second derivative is negative. Are we cool with that? Okay. And then this point of inflection, like I just said, is that is the point of the graph of a function has a so the graph of the original function has to have a tangent line, and where the concavity changes the point of inflection. So that's a weird little subtlety that will kind of come up from time to time. But in order to have this point of inflection, second derivative 0, but then also you have to have a tangent line there. You'll get this on the original. So like tangent lines off of the original function. So meaning something has to exist there. Because in a lot of places, if the second derivative doesn't exist there, then kind of the third derivative is definitely like falling apart there. Do you know what I'm saying? Because you have to take the derivative again. Okay, so like in this bottom little problem of our previous example, there's x cubed. We found second derivative is 6x. So then we did all that. The point of inflection is when 6x equals 0, and that happens at x equals 0. Okay? Any questions on that? What's this extra word? Yeah.
So the tangent line, it's just, or for the point of inflection, the tangent line, it has to, graph the function as a tangent line, so that means that the first derivative has to exist there?
Yeah, I mean, doesn't that make sense? You need to have a first derivative in order to have a second derivative, you know what I'm saying? Otherwise, it's like, you know what I'm saying? It's like, so I was talking to Estelle this weekend, you know what I'm saying? And I'm like, Estelle. I was hanging out with Estelle in South Beach, it was really nice. Just trying to throw some crumbs on. All right. I was like, Estelle, you got to do the second derivative test, otherwise it's just not going to work on your next album. Oh. She's like, I know. All right, so looking again at min-max points here. So here's what's actually really neat about the second derivative. So do you guys remember back in the day when we were doing the first derivative test from like 10 minutes ago? You guys remember? So in order to find a min-max, what you can do is find the critical point and then use the first derivative, test to the left and test to the right. If it goes from increasing to decreasing, it's a max. If it goes from decreasing to increasing, it's a min. Yes? Do you guys remember that? So that's the first derivative test. When what you need to do is find the critical points, list them out, make a little sign chart, and check for positives and when the derivative is positive and negative, and then you can determine that. Okay, so you got to plug stuff in. This is way better than that. This is super cool. Second derivative test for local extrema. If you want to test if something is a min or a max, one is you do the derivative to find the critical point. And then what you do is you take the second derivative and plug that critical point into the second derivative. And here's what this is going to show you. So here's a whole bunch of stuff. But check out, and I'll even do x squared, but here's a picture of x squared and negative x squared. You guys see them both there? I mean, it could be anything, just put a C there, but let's call it x squared and negative x squared. F of x equals x squared. Its derivative is 2x. Critical parts are when the derivative equals 0. And that happens in this case at x equals 0. Okay? So again, what we did in the previous example was we checked to the left and to the right. This thing went from decreasing to increasing because negative derivative and positive derivative. So it's a min. But check this out. If I take the second derivative of this function, 2x, what do I get? 2. If I plug in that x value, which is 0, into the second derivative function, what do you get? 2. A positive number. And here's what, there's no sign chart needed for a second derivative test. Here's what you do. You find your critical point, x equals 0. Do you know that is a candidate for a min or max? You plug it into your second derivative. Well, this thing's always positive. There's really nothing to plug into. But this shows you that this graph is always concave up. what does it mean if you're concave up at a critical point? Min. Does that make sense? So you just plug in and check the sign on the second derivative. If you have a critical point, and you plug that critical point, just that x value, into, because see, it's all concave up. You see, it's not just, it doesn't change at the min. It goes literally like this and this, so it's all concave up. So at this point, you'll get a positive second derivative. It's not changing there. It's not an inflection point. You see what I'm saying, Eleanor? So what it is like a do it for the critical point, and then plug it into second derivative, and bam, so there's no sign chart needed in that case. Okay? And if you take like negative x squared, which would be a case like this, negative x squared, the derivative would be negative 2x, same critical point 0. You take the derivative of that, second derivative is negative 2, which means it's always concave down. Second derivative is always negative. So at that critical point, the second derivative is negative, which makes it a max. Does that make any sense, you guys?
Will that always work?
Yeah.
So
You don't have to. But so here's the thing, it's like always depends on like what information you have. What if you just have a table of values that's just derivative values? Just be able to use, first derivative test. But sure, if you can't, isn't it just so much easier just to do the second? It's like boom and boom, it's positive. Okay, it's a min. But definitely a lot easier. Yeah, there's less like setup involved. But depending on what information you have, you may not be able to take a second derivative. You know what I'm saying? So you just have to do something else. And just, be aware of both. Make sure both go on the note cards. Because again, that's what it is. Like you're presented a problem, and then just how do you solve this problem with the information given? Yeah?
What if the value of the second derivative is 0, like in x cubed? Like the critical point would be at 0, and then you put that into, half double times 0 is 0. That's neither one of those. It's not.
Is it a min or a max?
No.
What does it tell you then? You know what I'm saying?
Does it tell you nothing?
It doesn't, right? I mean, it would tell you that that's why it still worked. It's like if that second derivative was positive there, it would be concave up, which means it's a min. The test is saying, like, here's the test. If the derivative equals 0 and second derivative negative, like not 0, less than 0, then you got a max. You know what I'm saying? Both those two things together.
So what is it?
Huh?
So what is the critical point?
Well, what he's saying is x cubed is x equals 0 is a critical point. You know what I'm saying? So f prime of 0 and x cubed does equal 0. So that's good. But second derivative at that same point is neither of these. So it's neither a max nor a min.